Alright. So, vibrations and waves. A vibration is a periodic wiggle in time, meaning it's something that repeats itself periodically in time, or in reference to time. So, after so much time, you'll see it again. A periodic wiggle in both space and time is a wave. So, if you see something repeat itself and get back to the same spot, then it's or I should say, a wave moves while a vibration stays put. So, it repeats itself but in a different spot. That's the difference between a wave and a vibration. Vibration, when something's vibrating, it's not moving some other place. It's staying put. Whereas a wave travels. So, for example, a light is a wave. So a sound. Whereas a pendulum would mostly be considered a vibration. For the most part, we'll treat them identical. It doesn't matter if it's a vibration or a wave. Because you can convert any vibration into a wave. If you, we'll see in a little bit. For example, a pendulum, like a grandfather clock swinging back and forth. If you were to put a pencil under it, and then have a piece of paper that's slowly moving, it would draw out a sine wave. So vibration is a wiggle in time, while wave is a wiggle in space and time. So vibrations of a pendulum. If we, a simple pendulum can be constructed from a string and a piece of mass. If we suspend a stone at the end of a piece of a string, we have something known as a single pendulum. The pendulum swings to and fro at a rate that depends only on the length of the pendulum. It does not depend on mass. So just like when we have like a feather and a bowling ball dropping down, they fall at the same rate if we ignore air resistance. If there's no air resistance, everything falls at the exact same acceleration. Likewise, it doesn't matter for the mass of the bob on the end of the pendulum. They'll all swing at the exact same rate. The only thing it depends on is the length of the rope. Which, why is this useful? What can you do? What can you make? What can you use a pendulum for? Kind of said it a second ago. Well, what can you use a pendulum to do? What's up? Mm-mm. I mean, you can, but a clock, grandfather clock, you can make it very accurate. Since it only depends on the length of the string, all you have to do is have it set up to where you can readjust the string length, and you can build an accurate grandfather clock. That's the reason why grandfather clocks have pendulums. The only issue is due to friction, they'll slowly reduce over time. So the time it takes for it to repeat itself is called the period. So the time of 1, 2, and fro swing is called the period. The longer the length of the pendulum, the longer the period. Just as the higher you drop a ball, the longer it takes for it to reach the ground. So a 1 meter long pendulum has a bob with a mass of 1 kilogram. Suppose that the bob is now replaced with a different bob of mass 2 kilograms. How has the period of the pendulum changed? It only depends on the string, so it'll remain the same. Doesn't matter if you use a light bob or a heavier bob. Now, do note that in the real world, it does depend on mass, because friction depends on mass. Not air resistance, but the friction up on the string rubbing. also the shape of the bob can have more drag. But recall that for a pendulum, in an ideal setting, we'll assume it's ideal, it only depends on the length. Now, same situation, we have 1 meter long pendulum and a 1 kilogram bob. What would happen if we double the length of the pendulum? Yes. So that's because it's now having to do more distance traveled. So if we look at a pendulum and we were to see it bounce back to right here and then bounce backward, we can see that if we were to extend this, double the length, that it would have to travel a much greater distance if we doubled it. So the time it takes to travel this extra distance, it makes it go slower. Let's see if I can remember the equation. So period of pendulum. Also known as the oscillation of a pendulum. An oscillation is just another way of describing a vibration. Alright. So the equation, how good are y'all at adding an infinite number of numbers? Y'all can't add an infinite number of numbers? Oh, geez. There we go. Also, multiplying, factorials. Here's the equation. There's a nice trick in physics. So, what does a sine curve look like? Do y'all ever graph sine function? So, sine of x. Y equals sine of x. This is y. This is x. It looks something like this. Right? Where this is 1 and this is -1. Now then, if I draw, let me just use a different ink. I draw y equals x. What do you notice about y equals x and sine of x? They are very, very, very similar for small angles. So if you're letting x be an angle, then they're very similar for small angles. This is known as the small angle theorem. Sine of theta is approximately equal to just theta for theta, and these are in radians. These two less than symbols means much greater, much less than. So basically, sine of theta and theta can be treated as being equal for small angles of theta, and they have to be in radians. So we can see thetas in here. We can see a very so this is the equation. If you expand it out, it's an infinite sum, large numbers. But if we recognize that theta and x are about the same, so if we use the small angle theorem, we can approximate the period using this simple formula. So this only so let me, no, y'all can't see it. Alright, so oh wait, is the angle theta the half angle? Yeah, it's the half angle. I had drawn up. So if this angle here is significantly less than 1, we can approximate the period like this. To give you an idea of what 1 radian is, 1 radian is 60 degrees, approximately. It's 57 point. So it has to be significantly less than 60 degrees. So really, this only works for pendulums that look more like this. If you see it move over like this, bouncing back and forth, then the time it takes for it to go all the way over and back to the original spot can be approximated using this formula, where L is the length of the rope. So L is length of rope. From one end point to center of mass of bob. G is the acceleration due to gravity. Which can be approximated as 9.8 meters per second squared to 9.81 meters per second squared. I flip-flop which numbers I use, 9.8 or 9.81. What this means is grandfather clocks are location dependent. If you were to move a pin, so let's say that you're in Italy, way back in the 1500s, and you have an accurate clock, and let's say that you move to England, or you move up into Switzerland, or Switzerland is actually known for some really fancy clocks. Up in the mountains, and then you move down where gravity changes. You could actually, you have to actually retune your grandfather clock because of the very small changes in acceleration due to gravity based on your altitude on Earth. Usually we can have a grandfather clock work on 2 different ways. We can have a grandfather clock so that every half period is 1 second, or we can have it so that every full period is 1 second. So, for example, if it moves here and then moves over here, We can either define this as being 1 full second. So 1 second, and then we can have it go backward, go all the way back, and have that have 1 second. In this situation, the total period would be 2 seconds. So recall that the period is the entire oscillation. So this will be a half period. So a half period. And this would be another half period. Together they make up a full period of 2 seconds. That's usually how clocks work. Let's solve for both cases though. So what length of rope do we need for the period to be 2 seconds? So if we look at our formula, and we're going to assume that's a small angle, we have the period is approximately equal to 2 pi times the square root of L over G. So we're trying to solve for length. We know that period is 2 seconds. We know that G is 9.8 meters per second squared. And so we need to solve for L. So we divide both sides by 2 pi, which cancels out on the right side. So we have T over 2 pi is equal to the square root of L over G. We're going to then square both sides. The square and the square root cancel, giving us T squared over 4 pi squared on the left side is equal to L over G. We also need to add in plus or minus, but we know that the length is going to be positive because distance can't be negative. And then we multiply both sides by G, canceling out G on the right side. And so we end up with the length is equal to G times T over 2 pi squared. Our length is equal to G T squared over 4 pi squared. Whichever equation you think is easier to write. So if the period is 2 seconds, we see that the length has to be equal to 9.8 meters per second squared times 2 seconds squared over 4 times pi squared. Which corresponds to 0.99295 meters. So, almost perfectly a meter stick. So you can get, if you have a meter meter stick to measure one length, you can get a clock that has a period of 2 seconds, so that every half period is a 1 full second. If you want to do it for, what about for T equals 1 second? Well, we've already solved for the equation. length is equal to g times t over 2 pi squared. So that's 9.8 meters per second squared times 1 second over 2 pi squared. Which gives us 0.24823 meters. This would probably be your wall clock, if you have a grandfather clock. So in this one where it's 1 second, it goes all the way to the right, then all the way back takes 1 second. Whereas this one, it goes all the way to the right, takes 1 second. And then all the way back takes 1 second. This one goes all the way to the right and back in 1 second. And it's just depending on your latching mechanism, what causes the gear. This setup is usually right here, is attached to a gear system. And you can design the gear system so that every tick either is a back and forward motion, or you can design the gear system so that every tick is on a half period. This setup is, because it uses less rope, means you have to be very precise to make it this small. Whereas this system is what they usually did. That's why grandfather clocks, you usually see them, are at least 1 meter in height. Usually they're very massive, because you need 1 meter of rope for them to be accurate. A wave is pictorially represented by a sine curve. A sine curve is attained when you traced out the path of a vibrating pendulum over time. So if you had some sort of bulb that you can fill up with sand or ink, and you were to let the ink spill out of the bulb over time, again, mass doesn't depend on mass. It does depend on center of gravity, so the center of gravity is changing, so the length of the rope is getting longer. But as it drips out, if you have the paper moving at a steady rate, you'd be able to see a sine curve, just like you can see in this image. So when the bulb vibrates up and down on a spring, so we have a spring attached to some fixed point. If you pull down on a string and let go, the bulb will vibrate up and down. If you were to graph the motion of it, you would be able to see a sine curve also. So vibration and waves, they have crest, which is the high point of the wave, and troughs that are the low point. If you were to put an imaginary line in the middle, that is then the distance from that imaginary line to a crest or to the trough is known as the amplitude. Amplitude usually corresponds to energy. If you have a wave and you give it, the only thing you do is change the amount of energy, that energy would be stored in the amplitude. Wavelength is the distance from the top of one crest to the top of the next, or it's the distance between any two identical portions of the wave. Again, we've already covered this, I believe, last time, right? Yes. So, frequency. Frequency is measured in hertz, named after physicist Heinrich Hertz. A frequency of 1 hertz is an oscillation or vibration that occurs once per second, or 1 cycle, 1 oscillation, 1 vibration, 1 whatever per second. Mechanical objects, such as pendulums, usually have a few hertz. Sound can go anywhere from a few hundred hertz to several thousand hertz. I think human hearing, I will actually look that up. Human hearing. And it changes based on your age. Is between 20 and 20,000 hertz. So we can't hear anything under 20 hertz, and we can't hear anything over 20,000 hertz. But the older you get, that decreases. One thing a lot of students do is play a very high pitched sound. Because teachers wouldn't be able to hear it. But the students can. And I remember when we were in high school, someone would always do that. And it's like right on the edge. Like everyone in class is just complaining. The teacher's like, I don't hear anything. What are y'all talking about? And it's like as you get older, you lose the ability to hear the very high frequencies because of damage to your ears. They naturally get damaged over time. Also, if you listen to high music, you'll speed that up. You have your headphones on a loud blast. Radio waves are going to be in the few million hertz, and cell phones happen in billions of hertz or gigahertz. So it specifies the number of to and fro vibrations in a given amount of time. It's the number of waves passing by any point per second. So 2 vibrations occurring in 1 second is a frequency of 2 vibrations per second, or 2 hertz. You can convert between period and frequency easy. They are the direct inverse of each other. A period measures the length of time, and frequency measures the count in a period of time. So a period is how long one cycle takes. I'll actually write that because that's important. A period measures how many seconds it takes to complete one cycle. A frequency measures how many cycles are completed in 1 second. And this is using the assumption that our measurements are in seconds. We can have, of course, periods measured in other units besides seconds. We can have frequency in other things. So, for example, we can have frequency in RPMs, which is revolutions per minute, or radians per second, or some other unit. So a sound wave has a frequency of 500 hertz. What is the period of vibration of the air molecules due to the sound wave? Math's wrong. What is 1/5? 0.2. So you know our answers go up to 2. The zeros after the 5 only change where that 2 is. To convert to time, you just take 1 divided by the frequency. The frequency of a particular wave is 20 hertz. Its period would just be 1 over 20 seconds. So if something has a frequency of 20 hertz, that means it's happening every 1/20th of a second. Wave motion. So waves transport energy. They do not transport matter. So even though the matter is moving, they're repeating itself. A wave of vibration, remember, is periodic. It repeats itself. If you drop a stone in a quiet pond, the resulting ripples carry no water across the pond. Waves travel across the grass on a windy day. Molecules in the air propagate in a disturbance through the air. So in an ideal world, if you're out fishing and a boat were to go by, your bob on your fishing line will not move anywhere. All it will do is go straight up and down. As the wave moves, the bob will only go up and down. It will not move left or right. Water waves do not push an object in any direction. It just causes them to vibrate up and down. If we were to look at any bit of water and stare at it, we'd see every bit of water only moving up and down. So a wave like this, the particles repeat themselves. They don't actually move. What is moving, however, is energy. Energy is being transported from one location to another. Again, this doesn't actually line up with reality somewhat. The reason why is, let's say that we have a small wind blowing. Then the bob is obviously going to move because the wind's pushing on it. And let's say we have an undercurrent. If the current and the water down here is moving and the wind's blowing, obviously the bob's going to move. Another thing to recognize is if we were to imagine the bob sitting here in a wave like this is a slope. The bob is going to try to move down the slope. But whenever the wave flips, then we'll see here it's not moving. And then when it flips like this, we can see a slope and it should move back. However, there's a little bit of wind moving and blowing it. The wind's blowing and pushing on it in this direction. It'll more likely fall down this slope to the right, whereas the wind will keep it from falling down the slope, so it would eventually drift like that. But again, in high school, we'll assume we live in a perfect world. So wave speed describes how fast a disturbance moves through a medium. Related to frequency and wavelength of a wave, all it is speed or velocity of the wave is equal to its frequency times its wavelength. So a wave with a wavelength of 1 meter and a frequency of 1 hertz has a speed of 1 meter per second. 1 hertz times 1 meter per second gives you 1 meter per second. A wave with a wave length of 10 meters and a time between crests of 0.5 seconds is traveling in water. What is the wave speed? Mm-mm. So we're given the information of 10 meters. This is the wave speed. This is our wavelength. This is your lambda. But it gives you period 0.5 seconds. And our equation is that velocity or speed is equal to frequency times wavelength. We know that frequency is 1/, period. So that means our frequency is 2 hertz. So 2 hertz times 10 meters is 20 meters per second. Again, don't just take the numbers and manipulate them. Make sure you actually label your given information. So there are two types of waves. There are transverse waves and there's longitudinal waves. I'll show pictures of both. I really need to get Slinky for this class. Large Spring, it's very good at seeing the waves. You can produce both types in a Slinky. So the top is a longitudinal, the bottom is a transverse. So a transverse wave is your sine curve. The medium vibrates perpendicular to the direction of energy transferred. So, like the bob in a water wave would go up and down while the wave moves across the pond. So it's perpendicular to the motion of travel. Vibrations, so it's a side-to-side movement. Vibrations and stretched strings of musical instruments. These transverse waves are usually what we think of when we think of a wave. Radio waves, light waves. This is an important thing to know too. There's also called S waves when dealing with earthquakes. S for secondary or shear wave. There are two components of an earthquake, and they travel at different speeds and can penetrate different layers of Earth. It's actually, we use earthquakes to model the core of the planet based on the fact that it produces both transverse and longitudinal waves that move differently in liquids and solids and other things. They also travel at different speeds. I'll show some pictures later. So the distance between adjacent peaks and the direction of travel for a transverse wave is called the wavelength. And vibrations along the transverse wave move in direction that's perpendicular to the wave. Longitudinal waves are going to be things like sound waves. Medium vibrates parallel to the direction of energy transfer. It's a backward and forward motion consisting of compressions. So instead of troughs, we have compressions. And instead of crest, we have compressions. Instead of troughs, we have rarefactions. Rarefactions are the stretched regions between the compressions. These usually occur in gases and liquids. They can occur in solids too. It's a compressive force. It's better seen with a picture. So they're also called the P or principal or primary waves of earthquakes. If we were to visualize all the air molecules, whenever we're talking, what's happening is as you push air out of your lungs, it causes the air to bunch up and it acts like a spring. As the air compresses, it acts like a spring, and the original air pushes back, while new air is pushed forward, and it does the same thing. It'll compress up, and then they'll push off of each other until causing the air in front to compress, and then it'll repeat over and over and over again. That's how it moves out. So let's see if I can get a good animation. So here's the difference between so a spring. So this would be a compression moving along. So this would be one wave moving along in longitudinal, while this is one wave moving along as transverse. Here again, so this would be transverse. The particles are moving in the same direction, they're parallel. So you can see here's a crest, corresponds to the compression here. You can use vertical lines to represent it. But there's one image in particular I want to show you guys. I think this is it. So this is a way, again, how your lungs work and how you speak is you have a voice box that changes the frequency of how much the air is moving in and out. It stops it basically, so you get higher frequencies. But you're basically pushing air, which causes, if we look, can y'all see like this single red dot? So it's following just a single particle of air. And you'll notice that a single particle of air is barely moving. This is every single dot on this paper is only moving this much. It looks as if you see a lot of air molecules moving quite a lot. In actuality, if you just follow every single dot on this entire screen, they're only moving this distance. It's just that you're seeing all move a periodic way so that you get these speeding movements like this. This is showing the case where you have waves, combinations of both. So you can have a longitudinal. Where's the other one? Nope. Also, we're in 3D, 3 dimensions. This one not open. One of these is really good at showing the dots. Yeah, that was it. So again, if you follow any individual particle, you'll see that they're not moving that much. But the wave as itself is actually moving. So when you're speaking or any air is moving, the actual matter is not being transported from one location to another. It's vibrating in place. It's just oscillating back and forth. The wave itself is carrying energy with it. And it's only energy that is moving. Where is... This is more like a sound. Alright, we'll continue tomorrow.